In this video, we're going to learn how to calculate average atomic mass using some isotope values. And in a lot of the questions, they're already given for you, so you don't really need to use your reference table. You will need a calculator, of course. And so one of the things that we want to pull out when we look at our formula is always going to be looking for the mass and the abundance. Now, the mass, of course, could either be a rounded mass, it could be a mass number, or it could be with a decimal value, depending. Sometimes you'll get both, but if you're going to do it, stick with one all the way through versus mixing and matching. So for example, if we look at this, I have boron 10 over 5. The atomic number of boron is 5. We don't really necessarily need that for this equation, but the isotope for boron, we have boron 10 and we have boron 11. Notice I have other values, 10.01 and 11.01. Now notice in this case I have both values. I have 10 and 10.01 and 11 and 11.01. You can use one or the other, and it would just make sense to be consistent all the way through. So when you're doing your calculation, use the 10 and then the 11, or use the 10.1 and the 11.1. So be consistent using both of the actual values or both of the rounded values. It's a lot easier just to use the rounded values, but I'm going to show you some calculations just showing you with this, and really it's just a difference of maybe how specific your answers are going to be and into what decimal value. So it says their masses based on a carbon scale, or on the carbon scale, are 10.01 AMUs and 11.01 AMUs respectively. The isotopic abundance of boron 10 is 20% and boron 11 is 80%. What is the atomic mass of boron? So we need to take the mass times the abundance, and then we are going to add that to another mass times abundance. And we're going to do that however many times we have. Now in this case I only have 2 isotopes, so I only need to do it twice. But in this example, the next example, we'll see there's actually 3. So when we do this, we're just going to take 10.01, that's my first mass, and my first abundance, the abundance of 10 is 20%. But remember, we can't multiply by a percent, we got to convert to decimal. So 0.20 is 20% converted to a decimal. Now if you forget how to convert percents to decimals, all you have to do is move your decimal 2 places to the left. Okay, every time you move it 2 places to the left, and that's going to be something of importance when you get into smaller single-digit decimals, or even percentages, and even percentages that are in decimals already. So when I get that value, I'm going to do this math, and I get 2.002. The other value, we have 11.01 times 80%, or 0.80, which when we do the multiplication, 8.808. When I add those two up, I get 10.81, and our unit in this case would be AMU. And if we pull up boron in our reference table, notice there we have 10.81. So that's how the average mass is calculated. These values you see here on the tops, like carbon 12.011, 10.81 for boron, it's called the atomic mass. Now really it's the average atomic mass. Okay, it says atomic mass, but really it's the average. So if we were to take all of the atoms of carbon together, this is what it would average. Most carbon is carbon 12, but there's also radioactive carbon 14. There's carbon 13 as well. And so that's one example. I'll do one more, and then you should be able to kind of grasp the idea of what we're really looking for here. And so silicon has 3 isotopes. We have 28, 29, and 30. And notice I have rounded numbers. So 28 would be 27.98 rounded. 29 is 28.98. That would be rounded up, and so on and so forth. And there's our 3 respective percentages, 92.23, 4.67, and 3.10. So this is where people make mistakes because they don't move it over 2 places and they might have an error. When you look at your final answer, like my final answer here, 10.81, had to fall in between 10 and 11. If I have an answer that is lower or higher than any of my values, then I know I've done something wrong and I got to go back and check. And a lot of times it's the error right here. They forgot to convert into the proper decimals. So when I do my setup, we're going to use these smaller numbers just to keep it simple. So for example, if we have 28, actually I take that back. We're going to use the full number because I'm looking at my other answer key here. So 27.98. And we're going to set that up in a percent. We have 28.98, and we have, and this should be a plus in between, and then we have 29.97. But then we have to multiply them by their percents. So my first percent, 92.23, if we move our decimal over 2 places, 0.9223 which is 25.806. If we have 4.67, we got to switch that over twice. Remember, put that 0 in there, so it's 0.0467. That's where people often make an error. And then again, 2 places over, we want to make sure that we get that other 0 in there, 0.0310. And so when we do the math, make sure you're seeing this. This is 1.353, and this is 0.929. So again, it would be those two multiplied gave me that, these two multiplied give me this, these two multiplied give me this. When we do that whole math, we add those 3 up, 28.09 AMUs. Now, when we go through and we check our math, notice 28.09 is in between 28 and 30, and it makes sense because it's closer to the 28 number, because most of them were 92% were the silicon 28 isotope. So when you do your math should be closer or closest to the value of the isotope that you see the most. So hopefully you found value in the setup. A lot of times New York State will just say show the correct numerical setup, and if I had something like this, that would be the correct numerical setup. On the top question, my first part, this would have been the correct numerical setup. That's one way to go about doing it. And again, the key thing is going through and converting your percentages into decimals. Now, another way to do it, if you did not convert your percent into a decimal and you just left it as 80%, your final answer needs to be divided by 100. So keep that in mind. So I always like to teach them and train them and get them used to converting into a decimal so we can get those real numbers right off the bat. So hopefully that's helped with your calculating atomic mass. Make sure you take some action on the other questions, and if you have any comments, just be sure to leave them below.